Okay, so here we take a look at the spring mass system. How could we write the ODE to describe the spring mass system? Okay, so here, suppose we have a wall, and then there is a spring with a coefficient k. Okay, and then it connects to a mass. Okay, m, like this. Okay, so even in high school, you know F equals kx, or I would say F equals negative kx. Okay, to describe this this spring. Okay. Okay, so which means that if we try to drag this mass to a displacement x. Okay, suppose this is x. Okay, so there will be a force F. F equals negative kx acting on it. Okay, and then negative kx acting on it. So according to the Newton's second law of motion, you know that F equals negative kx equals ma, of course. F equals ma is Newton's second law of motion. Okay, so ma is is the form we learned in high school. So actually the acceleration is the second derivative of the displacement. This is displacement. Okay, so we try to change the variable, so it becomes m d2x dt2. So the acceleration is the second derivative of the displacement. Okay, so we try to see here, this one is equals to this one. Okay, so we try to move over the terms on one side, so we have m d2x dt2 plus kx equals 0. Okay, so you can see this is a second derivative. This is the original function. This is a constant. This is also a constant. So we try to divide m on both sides. Divide m on both sides. So m and m cancel each other. We have d2x dt2 plus k over m x equals 0. Okay, so we try to write out the characteristic polynomial. This is a second order, second derivative. So we change it to s squared, and then plus k over m is a constant, and then kx, this is the original function, we change it to 1, okay, equals 0. So k and m are positive value, so that this is a positive value, which means that s squared equals to a negative value, which means that s should be plus or minus j times square root of k over m. Okay, so this is so this is the root, okay, which means that x should be something like a, or maybe we can just call it, we can define it to be plus or minus j omega. Okay, omega, this is the oscillation frequency. This is the oscillation frequency. So it is like a cosine of omega t plus b sine omega t. Okay, or you can just write it as r cosine omega t plus phi. So this is the phase, this is the phase, this is the amplitude. Okay, so you can see this spring mass system with this second order ODE. This LC oscillator with the same form. Of course, this is V, that one is X. Here it is 1 over LC. This is K over M. So you suppose you try to change the corresponding variable, then yeah, you can convert the solution to each of them. Okay, so next we can see also Q, the charge, also take the same form. And also you can see I equals dq dt. I equals dq dt. So you plug in this one to here, you dq dt, so it becomes q dq dt cosine become negative sine of omega t plus phi, and then don't forget the chain rule. You need to take the derivative of the argument of the sine function. So take the derivative of this one. This is a constant, becomes 0. This one, omega t, you take d omega t dt, so it becomes omega. Okay, so altogether we have negative omega q sine of omega t plus phi. Okay, so which means that the charge and the current, this is the current, have the same frequency, omega equals 1 over square root of LC. Okay, the phase will be different. The cosine and sine will have a 90-degree phase shift from each other. You can see, just say sine is something like this, cosine is something like this. So between them there is a 90-degree phase shift. Of course there's another negative sign, so yeah, it will feel like originally this is the if a cosine of t, and then this one is sine of t. Okay, cosine is leading by 90 degree. Okay, cosine is leading by 90 degree, but here we have a negative sign. It feels like this one is leading by 90 degree. Okay, so this is the current. This is the current, and then we can try to find the energy stored in the E field and also the B field. Okay, so in the previous page we have Q equals capital Q. Capital Q is the amplitude, of the charge. So Q cosine of omega t plus phi. Okay, so keep in mind we have Q equals capital Q cosine omega t plus phi. Okay, so you plug in this one into here. So we have Q, capital Q square over 2C, and then we have also this cosine square. And for the magnetic energy is like UB equals 1/2 Li square. So here we have I equals this expression, I equals negative omega q sine of omega t plus phi, like this. So so we will have 1/2 L I square. I square is actually this one. So we will have here 1/2 L and then omega square q square, like this, and then sine of square of omega t plus phi, like this. Okay, of course here they are a little bit different. This is 1/2 L omega square q square. This is q square over 2c. So actually they are the same thing, because omega equals 1 over square root of LC, which means that omega square equals 1 over LC, which means that 1 over C equals omega square L. So you can see here, this is 1 over C. Okay, here we have omega square L. Okay, this is q square, this is 1/2. Okay, so these two are actually the same thing. Okay, but the point here is that here we have, this is q square over 2c, this is q square over 2c. So when we try to add them together, UE plus UB is actually the total energy. So we should have U is the total energy equals UE plus UB. And then it will come out with the very famous identity in the trigonometry, which is a sine square plus the cosine square with the same argument to be 1. Okay, you should know it very well in high school mathematics. So finally, it turns out to be q square over 2c. Q squared to be over 2C. So Q is the amplitude, so it is a constant, and then C is also a constant. So it is actually a constant. So which match what we have assumed at the very beginning, because we assume that U is a constant because there is a conservation of energy. So the total energy shouldn't change with respect to the time. So it should be a constant. Okay, so it says the maximum value of UE and UB are both Q squared over 2C. And then second, at any instant, the sum of UE and UB is equal to Q squared over 2C, a constant. And then third, when UE is maximum, UB is 0 and conversely. Okay, so there are some observation. Okay, so here we can see a sample problem. So it says a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is then disconnected, and a 12 millihenry coil is connected in series with a capacitor so that LC oscillator occurs. So this is an LC oscillator, this is the inductor, this is the capacitor. Okay, so what is the potential difference VL across the inductor as a function of time? Okay, so of course we should have something like a D2Q dt2 plus 1 over LC, and then this should be a small q equals 0. So we should have Q equals cosine, capital Q cosine of omega t. Here omega is actually 1 over square root of LC. Okay, we just skip the phi there. The phi is not that important here. Okay, so here we just make phi to be 0. Phi to be 0. Can always find the reference point. Okay, sometimes you can find it, but usually you can find it. Okay, so actually Q equals C times V. Q equals C times V. So C is here 1.5 times 10 to negative 6 power. And then V is 57 volt. So times 57. This is actually 8.55 times 10 to negative 5 coulomb. Okay, so we know this value. And so actually we would like to find a VL of t, which means the potential difference across the inductor. Of course, in this circuit, it is like this is L, this is C, and then this point connect to the ground. Okay, so you can either choose VL should be something like this. VL should be something like this. So actually, we also know this is the current, or maybe the current is the other way around. Maybe this is the current. This is the current. It's just up to. For this question, it's just up to you because it does not show a figure to you, so you can try to draw it favorable to you. Okay, so you can just feel like VL should be L di dt. So this is the VI relationship for the inductor. So you can always remember this one. But here we only know Q, and we know I equals dQ dt, which means that it should be like d dt, and then we change I to be dQ dt. Okay, so this is actually L, the second derivative of small q dt2. Okay, so here we can just plug in this one into here. So we have L, take the second derivative, it should become let's say negative, and then we have a q, and then we should have omega square. Cosine will change to negative sine, and then sine will change to cosine. So it turns out to be negative cosine. Okay, negative cosine of t. Okay, Negative Q omega. Q is from here, and then omega square is from the chain rule here. So we have negative Q omega square cosine of omega t. Okay, cosine become negative, sine become negative cosine. So we have negative cosine. Okay, so we can just plug in all the values, or we can just try to somehow simplify it. So we have L, negative L, Q, and then omega square should be 1 over LC. Okay, omega is 1 over square root of LC. So omega square is 1 over LC, cosine of omega t. Okay, so we can cancel L and L. So it turns out to be negative Q over C cosine of omega t. Okay, so it turns out to be negative 57. Negative 57. Q over C is actually V. It's actually V. Okay, so, and then cosine omega t. So t over square root of LC. L is 12 times 10 to the negative third power. And then C is 1.5 times 10 to the negative 6, like this. Okay, so finally it is negative 57 cosine of 7,500 T volt. Okay, so actually the SI unit here, this is radian per second. Radian per second is the angular frequency. Angular frequency, 角频率 radian per second. Yeah, radian per second. Something like this. Okay, so this is for question A, and then we have question B. What is the maximum rate di dt max at which the current I change in the circuit? So before we would like to find di dt, first we would try to find I equals something. Okay, of course we know Q equals capital Q cosine of omega t. So I should be dq dt. Okay, so Q comes down, and then cosine, the derivative of cosine become negative sine of omega t. And then don't forget the chain rule, so we need to multiply by omega. Okay, so this is I. Okay, of course we need to find di dt. So we need to take di dt. Okay, it becomes this one come down, so omega q, and then we also have the negative sign. And then the derivative of sine of omega t should be cosine of omega t. And then still we need the chain rule, so we need another omega. So we have omega squared. Okay, so here we would like to find what is di dt max. Di dt max. Okay, so we know this is a constant. This is a big constant. And then cosine is actually cosine of something is actually less than or equal to 1 or larger than or equal to negative 1. Which means that if we need to take the maximum of the whole thing, we need to have this thing equals to negative 1. Okay, to cancel this negative sign. So the maximum value should be omega squared q. Here cosine of omega t equals negative 1. Okay, and then we can just plug in the number, or we can just make it like omega squared is 1 over LC. So we have a q over LC. And then q over c is actually v. So it is nothing but v over L. V over L, because here q over c is v. Q over c is v. Okay, so finally it is v over L, which is 57 over L is 12 times 10 to negative third power. So this is 4,800. So what is the SI unit? SI unit for the current is A. Current is A, ampere. and then t is s, time is s, so A over s. Okay, so next we talk about the more difficult thing, which is about the damped oscillation in an RLC circuit. So just now we only have L and C in series. Here we also considering the resistor here. So of course it doesn't necessary to have a real resistance there, but actually for the circuit it should have some resistance over the wire. So we just model the whole resistor for the loop and then make it like a discrete resistor. We don't really add a resistance there. Sometimes maybe you will, but yeah, but here we consider the intrinsic resistor there. Okay, so you can, yeah, so when you just look at the bottom part, you can see the things become more complicated, of course, because we have an additional thing. So let's see. So at the very beginning, it is the same thing. The total energy equals UB plus UE. Okay, equals 1/2 Li squared plus Q squared over 2C. It is just as what we got for the LC oscillator, because the resistor don't really store energy. Okay, so the total potential energy is the energy stored in the B field and E field, which is stored in the inductor and the capacitor. This one don't store energy, but it consume energy. So here, rather than du dt equals 0, we have du dt equals to a negative value. Okay, if you still remember, the power of the resistor is like I square R. The power consumption. If there are current going through it, okay, I, so the power dissipation, the power consumption of this resistor should be I square R. Okay, so here du dt is actually the power. And here we consider that yeah, as much as the resistor is consuming power, which means that the total energy should be reduced by the power consumption. So here we have du dt equals to negative. Okay, which means that the total energy is decreasing. Okay, total energy stored is decreasing. Okay, the total energy is decreasing. Okay, so similarly, we can just take the derivative for this one, and then it should be equals to this one, negative I square R, rather than 0. Okay, so you can imagine just now we have this term and this term correspond to these two things. And of course, there are some cancellation. Okay, so finally, this term, maybe make it like this one will become this term. I'm not sure whether you want me to go through it again. If yeah, otherwise you can try to practice it at home if you have interest. Yeah, if you can really derive these two equations to here, then I think your calculus is quite good. Okay, but yeah, you can try to just follow the mathematics. Try to follow the mathematics here. Okay, if you can derive this one to here, okay, actually this one is the one we like, Li di dt plus Q over C dq dt equals negative I square R. Okay, and then you can see, this is I, dq dt is I, this is I, so one of the I cancel, and then that is negative. For that one we have a negative I square R. So one of the I cancel. I do not try to override it. So one of the I cancel, this dq dt cancel, and then this I cancel. Okay, so this di dt becomes the second derivative. And then of course the whole thing divided by L. So we have a Q over LC, which is this one. Here we should have I R over L. I is dq dt. So we have R over L dq dt. So you can see here. R over L dq dt. Okay. So you can try to refer to the previous thing. I don't try to write it out. Okay, so you can get this still second order ODE, but due to this energy loss, we have the first order term, which make it a little bit more difficult. Or you can imagine, or the solution look like this. We have an exponential term here. Previously, we only have the cosine. Okay, this cosine will go forever. But here, as much as this is exponential to a negative thing, R is positive, L is positive, we also consider that T is a positive value. So it is just like something like this. This is the exponential to negative R over 2LT, and then it looks like this. It looks like this. Okay, so it is called the damped oscillation. And then the oscillation frequency is a bit smaller than this omega. This omega is of course 1 over LC, 1 over square root of LC, if we don't have the resistor. Here we have a resistor here. So the oscillation frequency is a little bit lower, reduced by this term. If R is 0, then this term to be 0, and then omega prime turns out to be square root of omega square, which is omega. But here R is not 0. So this is a small term. We consider this is a small term, but so this whole thing will be a little bit smaller than omega. Of course, I will consider it in the potential method, in the potential method, which is what I learned before. Okay, so we can see how we can derive the same thing with the potential method. Okay, so here we can define, this is VL from here to here, and then this is VR, this is plus minus, and then VC plus minus, and then I takes this direction. Okay, so all the things are positive, so it is like VL equals L di dt, and then here VR equals I times R, and then for this one I equals C d VC dt. Okay, so we can just write out all the thing we like, and then as much as I follow the direction from positive to negative, so we don't have a negative sign. So I intentionally define like this. So this is plus minus, plus minus, plus minus, back to back connection. So using the KVL, we can actually write VL plus VR plus VC equals 0. Yeah, because plus minus, plus minus, plus minus, which is like a voltage drop, voltage drop, voltage drop, going for a loop. Okay, so VL plus VR plus VC equals 0. Then we can try to change it to the same variable. Let's see how we can change it. Okay, so first of all, VL is this one, so why not plugging it there? So L di dt, and then plus VR is IR. VR is IR, so we just put it there. And then VC is this side, we cannot change, so we just keep this VC here. Okay, so So the idea is that we should try to eliminate I, which means that if we just plug in I by this thing to here and here, okay, you can see this is I, this is I, this is I. So we change it to this C dVc dt. Okay, so for the first term, L times C, and then the second derivative of Vc, Vc. And then plus, this is R, this is C. So we have RC dVc dt, and then plus Vc equals 0. Okay, so we can just multiply 1 over LC on both sides, so we can normalize the second order coefficient. So we have a d2 Vc dt2 plus R over L dVc dt plus 1 over LC Vc equals 0. Like this. So we can get actually the same ODE as this one. Of course, this is Q, but as I mentioned, this is a linear ODE. So no matter which variable you pick out, you just plug it there, then it should be correct. Okay, so why the solution will look like that? Okay, because we try to solve this one. We don't have anything on the right side. This is already a homogeneous equation. So we just try to change the second order into S squared and then plus R over L, and then this is the first order, so we change it to S and then plus 1 over LC, and then this is the original function, change it to 1, so nothing here, so equals 0. So this is a second order algebraic equation. Okay, so which means that this is a second order equation, and then there should be three cases: the b squared minus 4ac larger than 0, equal to 0, or less than 0. Okay, so we just ignore b squared minus 4ac is larger than or equal to 0, because for larger than 0, it will feel like when b squared minus 4ac is larger than 0, it is like Vc equals a exponential to s1t plus b exponential to s2t. So this is just exponential decay. Usually s1, s2 will be negative if the circuit is stable. Actually here we don't have any active component. All the RLC are so-called passive component, 被动的元件. So they won't make the system unstable. So S1, S2 will be negative. So so it's just like exponential decay. So we don't really care about. And then for the next one, b squared minus 4az is equals to 0. Vc will turns out to be a plus bt exponential to s1t. Okay, if you still remember. Okay, so we don't like this either. Yeah, because if it is stable, s1 is a negative value, so it turns out still to like exponential decay, so it is not oscillating. So that's why, as I mentioned, usually the most useful thing is the most complicated one, which is like b squared minus 4ac is negative. Here, in that case, the solution will be 2, and then here we have a negative R over L. Okay, negative b plus or minus square root of b squared. B squared is R squared over L squared minus 4ac, like this. And here we assume this part is negative. This part is negative. Okay, so we can write it as, here we have a negative R over 2L and then plus or minus. Okay, so we just flip it and then make it a J here. And then we also put this 2 inside. So if we put the 2 inside the square root, it becomes 4. So here we should have 1 over LC, 1 over LC. Here we have 4 over LC, so divide by 4, so becomes 1 over LC, and then we just make it a negative sign out, so that the inside thing will be a positive value. Okay, so here we have a R over 2L quantity square. Okay, so put this thing into here. So we have R over 2L quantity square. Okay, like this. Okay, so this is S, S1, S2. Then you can see that this is the real part, this is the imaginary part. This is the real part, this is the imaginary part. Or maybe I just use the pen. This is real part, this is imaginary part. Which means that if you just write it as alpha plus or minus j beta, the solution will become Vc equals, let's say, A exponential to alpha t, and then cosine of, originally it should be like cosine of beta t plus j beta t, and then we change it. Yeah, when I talk about the solution at that time, it should be like exponential to alpha t, and then let's say a cosine of beta t plus b sine of beta t, something like this. But here, as much as they are the same frequency, we can just change it to, let's say, an R. Maybe I just write it as a capital VC exponential to alpha t, and then cosine of beta t plus phi, something like this. Yeah. So alpha is actually negative R over 2L, and then this beta is the omega prime in the front. This is a beta. Beta is beta. Yeah, this is this one. So we have square root of 1 over LC, and then minus R over 2L quantity square. So here we can see omega square is 1 over LC, and then minus R over 2L quantity square. So this is actually the beta. And then you can also see this is alpha, this is beta. Of course this is Q, but yeah, actually VC or other variable will have the same form. Only the initial condition or just say the amplitude and the phase are different. Isn't it interesting? Okay, okay. So maybe let's take a 5 minutes break.